Hello, I welcome you all to this another interesting screencast. The problem reads a ball A is thrown vertically upwards with a velocity of v naught. Ball B is thrown upwards from the same point with the same velocity t seconds later. Determine the elapsed time t less than 2 v naught divided by acceleration due to gravity from the instant ball A is thrown to when the balls pass each other, and find the velocity of each ball at this instant. This problem is coming from the Engineering Mechanics Dynamics 14th edition by R.C. Hibbeler. So we have two balls, ball A and ball B. Again, here we are dealing with rectilinear motion. This is motion in a straight path or straight line. Right, so here balls are being thrown vertically upwards. Let's draw what is happening. We need to let's draw something so that we can relate. So let's say this is our datum. So let's say I have ball A in red, something like so. It goes up. Let's say it goes up to somewhere there, then it comes down. Okay, comes down. Let's say it comes down. Then let's say ball B is thrown also upwards like so. Let's say maybe up to somewhere there, but we know it is going to go up like so, then it will come down as well. Let me also finish this line. Just finish this line to eventually come down. Okay, not take a line like so. Right, so this is what we have. Let me dot this. I'll dot this, let's say up to somewhere there. Okay, and then let me also dot this. I'll start from here going round like so, up to down there. Okay, so let's say we have this ball thrown. It is thrown. This is the ball thrown. There it goes. It is going up, and then we have this point where the velocity changes. Okay, it becomes 0 at that point. Okay, and then it comes down. Then we have this ball here. Okay, so this ball is moving like so. Okay, there we go. Then we have this ball here. Okay, so this is our ball A. Right, this is ball A. This is A. So it is thrown like so, and then of course eventually it will come down. But we are not interested at the point where it comes down. We are interested at the point where it meets with the other ball. So let's say we have another ball also thrown at the same velocity, but after t time. So we do have this ball like so. There it goes. There it goes. And then we have it somewhere there. Okay. Something like so. Right. Of course, we expect this ball later on it will go through this same motion, so it's going up like so, like so, like so, and eventually it will come down. Okay, but we are interested at this position, ball B. All right, so this is ball B, this is ball B, this is ball B. Okay, so we are saying these balls are thrown in a way that there's a lapse of time t. Okay, so there's going to be a point uh, when its displacement is the same. Okay, so this is S, where S is equal to SA equal to SB. Okay, right. And also, like we said, ball B is thrown after time T has elapsed. So see ball B, that's when it is going, right? That's when it's moving. Maybe I make this line thick. This is when it is moving. Let me make it a little bit thick in green. This is when it is moving, right? Like we said, okay? While this one, it has already moved like so, and it has come to this point. Okay, so this is basically what is happening. So now we need to find the velocity, I mean the time elapsed, and it has to be less than 2 v naught divided by g. Okay, so this is what is happening, right? This is what is happening. So let's find the time that the elapsed time from the instant ball A is thrown to when balls pass each other at this point. Ball A will be going down while ball B will still be going up. So we need to find this displacement. We also need to find the time. Of course, displacement will allow us to find the time and the velocity. Okay. So I talk about just 3 basic kinematic equations that we need to always remind ourselves when we are dealing with problems like this. 3 basic kinematic equations. What are these? These are, we have the instantaneous velocity, time derivative of position. Then we have instantaneous acceleration, which is time derivative of velocity. And then if we made the t subject of the formula, then we equated the two, then we'll have another equation, this one. All right. And then from these 3 equations, we are able to derive 3 more equations. And these are equations when acceleration is constant and t is equal to 0. And at this point, we have S naught and V naught. And the equations that we derive are S equal to S naught plus V naught by T plus half AC T squared. Then we have V naught plus AC by T. And then finally we have V squared equal to V naught squared plus 2AC by S minus S naught. So these are the 3 basic equations, and the other one derived when the acceleration is constant. So which of these equations do you think we're going to use? Because for me, I'll go for this one. Okay. Right, so let's say we have let me just create a kind of boundary, something like so. Okay, there we go. So let's say the first equation, we have SA. Okay, this is for ball A. So let's deal with ball A. So let's say case 1, we deal with ball A. Okay, so with ball A, let's find the displacement. Okay, so everything else will have subscript A. So we have the displacement SA equal to S naught A, but they are all starting from the same point, and then we have plus V naught, and V naught is the same. At this point, V naught is the same by T. So say TA plus, instead of putting a plus there, since our G is minus, is going up against gravity, gravity is coming down. So we'll say minus half G T A squared. Okay. All right, so here we go. So this is the equation for ball A, right? But we know that our initial displacement is 0, and therefore this just becomes SA is equal to V naught TA minus half G TA squared. Okay, so this is for case case 1 for the ball, and then let's go to case 2 for ball A. Let's go for ball B. Okay, and then we need to equate the two. So what do we have for ball B? So ball B is SB, we call this SB, S naught plus V naught, like we said, is the same. And then since there is the time in between when the ball was thrown, okay, then we'll say TA, to account for that, we need to get the difference, right? Minus B, like so. Then minus, because gravity is negative half G, and then we have TA minus TB. Okay, since we want to equate the two displacements, we need to account for the time. Okay, so we are subtracting TA because TA is much larger than TB, because there was this difference. We've seen this difference, this time difference in between. Okay, to account for that. Okay, so it is this time difference, TA minus TB is equal to this T, right? It's equal to this T. Okay, so there we go. So what do we have? So we know that S naught is equal to 0. Therefore, SB will be equal to SB will be equal to V naught by TA minus TB. Then we have half G. Then this we can multiply it in advance. This becomes T squared plus TA squared, TB squared, then minus 2A TB, right? Okay, so there we go. So now what we need to do now is to equate these two equations. Let's equate these two equations. Okay, so let me just create another boundary here. We create another boundary here. Let's equate these two equations. All right. Okay, so I also create another boundary there, like so. Okay, so let's equate these two equations. So like we said, SA let SA be equal to SB. Therefore, we'll say our V naught TA minus half GTA squared is equal to V naught TA minus TB minus TB and then minus half G by TA squared plus TB squared minus TB like so. So this and this part can go. What else? This part also and this part can go. So therefore, what do we remain with? We just remain with a 0 this side is equal to minus V naught TB. There, that one has gone, so we'll have a minus half over 2 G TB squared, and then a 2 and a 2 there goes. This becomes a plus G TA TB. Okay, so we can factor out the B, the TB, so it becomes TB minus V naught minus half G TB plus G TA. Okay, so at this particular point, TB is equal to 0. So let's find. Then we have this one equation where we can make TA subject to the formula. Right, we can make subject to the formula, right? Okay. Right. So we want to determine the time elapsed from the instant ball A is drawn to when the two balls pass each other. Right. So what? Right. So let's make TA subject to the formula here. So if we made TA subject to the formula, of course this equation becomes GTA equal to minus, it goes the other side, V naught plus half GTB. Therefore, our TA, if we divided both sides, becomes V naught divided by G and then plus just half TB. And of course, this is less than 2V naught divided by G. So this is the time. The elapsed time from the instant ball A is drawn to when the balls pass each other. Okay. All right. I think this is fine. Let me just move this a little bit up. I move this there, and then I move this a little bit up, maybe somewhere there like so. Okay. So now we are done with the first part. So what we need to do now is to compute. So here we are computing the time. Here we are computing the elapsed time. Okay, which should be less than the elapsed time, which should be less than 2V naught divided by G, which we've calculated. So here, let's now calculate the velocity. So the velocity of the two balls. So we calculate the velocity of the two balls, right? the velocity of each ball at this instant. Okay, so let's do. Of course, at this particular point, we are going to use this equation. We are going to use this equation to find the velocities. And again, here we need to take into consideration this time difference. Right, so velocity A will just be equal to V naught minus G times TA. Okay, we have the TA that we just calculated there, right? And then VB just equal to V naught minus G, and then this one here we are saying is TA minus TB. Okay, I think this is about it. Let's outline the final solution. So there we go. So we have this one here, and then we have these ones here. Okay, so I hope, there we go. Right, so I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.